Hello everyone, this is topic 6, designing with forces. Just taking a look at a few things that we're going to be doing here. First of all, we'll be able to demonstrate and describe methods to increase the strength of materials through changes in the design. And we're going to identify examples of frictional forces that can be used in the structures. First thing, there's a few things in the notes that you're going to want to put in. Engineers are going to do different strategies to prevent structures from failings, but some of the very common ones are, first of all, to study the features of the actual structure. And once you kind of do that, as you're studying those features, you're going to be analyzing the forces that are going to be the greatest, and then choose ways to counteract those forces acting on the particular object. So, how do we seek to counteract those forces? First of all, we're going to distribute the load so that no part is carrying too much. That can be with vertical supporting posts. Cylindrical columns are even better, and we'll talk a little bit about why, and using flying buttresses. So with a vertical supporting post, let's just say I've got a bridge here, and I'm going like this. With an object like this, what we find here is that there's going to be forces counteracted here, lots of force counteracted here, and not a lot of force counteracted here. Putting in an extra supporting beam can be used, that extra vertical supporting column can be used to hold up the weight. This really is used anytime we're trying to hold up weight. This is one of the things that we can do, is put in an extra column in. Of course, that does take up space. It does take up extra space underneath. And so depending upon what it is that you're doing, this may or may not be a big deal. It is also one of the simplest solutions. So this is the most simple solution. And it's usually the most cost effective. Okay, so this would be one of the cons, and these would be a couple of the pros as to why we might want to do the extra vertical column. Now, cylindrical columns are actually much better than rectangular ones. Now, rectangular ones are going to be cheaper, typically speaking, but a cylindrical column, if we think about torsion forces acting upon this, torsion forces are going to be a lot stronger, acting a lot stronger on a rectangular column rather than a cylindrical column. This uniform shape with the torsion force is really going to allow that force to be evenly distributed, where a torsion force here is going to wind up having areas of unevenness, and therefore spots where you're going to have more pressure than less pressure, and can lead to a lot more of that twisting that we could happen, a lot of deformations caused by the torsion forces. This is better able to resist. Now, the other thing is, because of the unevenness in a rectangular column as opposed to cylindrical column, this is more likely to buckle. This is going to take a force acting here straight on, and any sort of deformation, any sort of weakness here will more likely cause this to buckle than with this cylindrical post, and that's also just mostly due to the shape. A weakness here will not have the same impact as a weakness on a rectangular column. And so cylindrical columns are better able to resist torsion forces and buckling due to weaknesses. Okay, and so this is why we will want to use a cylindrical column. Now finally, flying buttress. It's a neat little thing. It's basically a support from the top to an outside support. So if we were to think back to this here, rather than maybe having a vertical supporting post, we might want to have put in, let's say, a flying buttress where it will come and meet at the side, Now, we don't use this very often. We've got other more compact ways to do it, but if you weren't worried about keeping the space inside, not worried about the space on the outside underneath here, a flying buttress may have been the solution. We see that as something that we see in trees. Old buildings looks kind of like this, where it's to support the top and to distribute the load. Instead of this load just coming under here and here, it's also coming under here and here. And so all of this load is being transported towards other support systems, meaning that we can leave this area quite a bit open. Okay, some other things that we would do is to direct forces along angled components, so the parts are held together, not pulled apart. This can be done with arches to direct forces along stones down to the ground. Domes or shells also do this. Or braces, which are direct forces on angles down the solid part of the structure. So if we think about arches, some old bridges, you may have noticed, even though they're flat on top, they're built kind of like this. Sometimes even today. What that's doing is the load that's here is being transported just through the nature of the structure over here. Now we've got water usually running through here. This is where the bridge is being supported, and so all the weight is coming over to where it is on land, as opposed to being held just straight here. And so an arch can be a very effective way of doing that. Arch doorways do the same thing. Anytime where you see an arch, that is what's happening. Another common thing we'll see is a brace. Thinking back to our table here, we've got object, object, object. Instead of us putting in a vertical column, we may want to put in a brace right here and right here. And it does the same thing. It's driving things down at an angle from where we would have seen the most force acting upon it, and relieving some of that stress, taking it to stronger areas. Right here we had the strongest areas. Now sometimes braces also appear kind of just like in little L shapes that are screwed in, which is saying, okay, you're just really focusing in at the places where these two pieces meet, keeping these pieces together, as opposed to worrying about here, where the angled ones will actually take that weight and angle it to where it can be better supported. A lot of times we'll see that with shelving. Let's say if we've got a shelving against a wall, if you're just worried about this area, you'll see that like slight L bracket. But bigger shelves, or ones that are designed to hold an upper load, will usually have some sort of bracing here in order for us to make sure that we can support the weight here down into the wall, rather than it just all being held at this one point. Now, shapes can withstand specific forces, Triangles generally are stronger than rectangles, or I, L, or T-shaped beams can help. Again, we kind of talked already about like an L-shaped brace, but you can see the same thing happening with beams. Now, an I-beam might look something like this. And the reason why we would use an I-beam is you kind of put in a wide base at the top, wide base at the bottom with a single supporting vertical column. The thing that happens here, as opposed to using a solid beam, is that this has less weight, thus less dead load. And we want to keep all the strength, so we maintain the strength with that vertical column, but reducing the weight or load acting underneath it caused by the size of the beam. And so we can see various beams, might be like a T-beam or even like a hollow box, as ways to reduce less weight, less load, but to keep the strength, depending on what it is we're looking for. Right? Rectangular shapes can easily be put out and pulled out of shape, usually with a shear force or a torsion force acting upon it, and so not upon it, within it. A shear or torsion force acting within it can cause most rectangular things to be pulled out of shape. Triangles don't have quite this same problem. Now here, one of the things that we can see, not only do we have a triangle within this roof, but we've got a vertical supporting column, as well as a couple of braces to come along here, and this brace probably would come all the way down to the bottom. And so you're transferring weight to here, here, and some of the weight is actually being transported to this middle vertical column. And so this will be one way that you're going to move the weight to the middle column through the use of triangles and braces. Okay, it's a sharing of the load, allowing you to bring things here. Here again, we can see vertical column, arch to where there's support. So for this high doorway, lots of, right? And you're constantly just trying to move the load to where it can be best supported. We see this happen in house construction all the time. Right. Load-bearing horizontal beams tend to bend, causing torsion and tension and compression forces acting within the object. And so using arches is one way that we can really support that. Transporting a lot of weight to the outside while keeping the opening. A cantilever is another one, which is where you're going to support it both from the top and the bottom to bring it to specific braces. Right, and here again we see the braces designed to hold some of the load as well as keep these joints in place from the beam to the post. Right, we're keeping this in place with the brace, but this is also taking some of the load from the beam to the brace. Again, if you're just worried about the joint, a little L-shaped bracket there could also be just useful. Depends on how much load it is that you need. Strong and heavy beams are expensive, but are another solution. A lot of times we'll even see people used an engineered wood, which uses a wide variety of wood types, all glued together, pressed together, engineered in a usually kiln, baked together in order for us to be able to create that. They are expensive, right? So the con is the cost, but they sure can hold a heck of a lot of weight. Right, here we see some of those L beams and I beams that we had talked about earlier. Again, hollow shapes can be helpful. Vertical column, this reduces the weight yet keeps all the support. Here we see, again, reducing the weight underneath, the load underneath that needs to be supported by the ground, but still managing to keep those vertical columns. Corrugations is another thing that can be useful in terms of transferring the load, and what you're really doing here is you're just constantly moving. That corrugations is really just a bunch of series of arches. Right, keeping things hollow, again, reduces the load while keeping the shape, and circular shapes, while it can be difficult sometimes to fasten things to them, do a better job at resisting buckling and torsion forces than their square counterparts. We'll want to take some time to strengthen structures as well, because not strengthening structures can cause some major problems. Here in the swing set, we see we've got supporting braces, arches across to support the triangular bases along the bottom. One of the things we'll want to do here is we will want to choose materials that best suit the features of the structures. This is something that's going to be very important for us in order to make sure that we're getting the proper resistance to forces. But we're not just worried about aesthetics here. We're worried also about the strength and being able to perform its function for a long period of time, keeping that quality up. Friction is important to keep things together. One of the things you may have noticed with the corrugations is that you can interlock corrugations, which is going to really increase the amount of friction. But nails and wood and screws, right? Different nails are going to have different amounts of frictions. The ones on right have much more friction, thus stay in place, than these ones, which will have less friction. Right? But with the finishing nail or a casing nail as an example, you're not actually putting a lot of support. You're just kind of holding something in place. Where the roofing nail or the masonry nail, you're really trying to make sure that you're resisting forces. Screws will even work better. They tend not to be as fast though. Okay, let's go through some examples. So designers have 3 key methods to help structures withstand forces. They include all the following methods. Well, A, B, and C are methods. D is actually not a method for resisting forces or withstanding forces. This is really just a method for reducing forces. Okay, this reduces forces, it doesn't withstand the forces, and so it's not for what the question has asked. In general, Roofs are going to use the triangles. We saw lots of triangles in the roofs to keep things quite strong. And what that's doing is it's going to direct things across angled components, right? Frame structure can support very heavy roof because one of the principles of design, the principle is visibly demonstrated by vertical supporting posts in the structure. This principle followed is distributing the weight evenly here by adding the extra post. When a structure has a single horizontal load, such as a beam supported by two columns at each end, that beam in the middle is likely to buckle. That bending exerts outward pressure on the vertical supporting beams. To strengthen this bridge, usually that additional column is probably one of the best things that we can do. Science fiction often gives us exciting ideas about materials that could stand almost any force. But one material that, if we could make it into the thickness of a pencil, would be so strong it could stop a jet plane. That is actually spider silk. Spider silk is the strongest material known on the planet, as far as I know, anyway. And one of the things that we'll want to be taking a look at. As we identify things moving forward, hand against the desk, you put your weight on them and try to move them forward, identifies the use of friction. A lot of times things will stick together simply because of friction. By interlocking shapes on the particle level is going to do that quite easily. Okay, so homework questions for this section, page 328, numbers 1 to 5. If you got any questions, let me know.